projection. We're gonna deal with circles today. Okay, so we'll be jumping around the text a little bit, primarily about in the middle of it, and look at how we deal with circular features. So to start with, let's jump. Before I go there, actually, let's do a quick review. Where did I start last time?
Up here.
Up at the front? Always, yeah. Okay, let's start in the back this time. Let's look for some definitions. Gabe, do you know the definition of a normal plane?
Normal plane?
Yes.
It shows up as like on the TVs, it's like a straight line on TVs, and it's like
Okay, yeah, that's it. True size and shape in one view, edge view in all adjacents, right? When you say a straight line, you're talking edge view, correct? Okay. So normal planes, true size and shape in one, look at adjacents, you get that line or edge view, you know it's a normal plane, therefore it's true size and shape. Get in the view, you see it. Declan, how about an incline? Plane.
I don't really know the definition of it. Oh, sorry.
We were just messing with one yesterday on your machine.
I know.
What was that plane?
Foreshadowing, is that what you said about it?
Mm-hmm. Yeah, that's part of it.
I'm trying to remember.
Okay, but let me help you out. You see it as an edge in one view, right? Just like a normal plane. It will appear as an edge on an inclined plane. But when you go to any adjacent view, then you will see it foreshortened. Okay? It will not be true size. Okay? And that's an inclined plane. Now that's going to become become important for our rotations for auxiliary views. So inclined planes. Edge view in one view, foreshortened in all adjacents. Okay? Sean, how about the last type of plane we encounter, an oblique plane?
An oblique plane is not parallel to your principal plane.
That's correct. Therefore, it will appear
It'll appear as an, well, it won't appear the same, well, how can I say,
it's that word we use with Declan. When we don't see it true size, we have to see it foreshortened.
Foreshortened.
Mm-hmm. Yep. And foreshortened is just a word saying we're looking at a plane and we do not see it true size. Right? So, and keep in mind, in orthographic projection, things cannot really, they can't appear larger than they are. They're either true size and shape or foreshortened, always.
But isn't it believed that you've never seen edge? You said?
Well, we do see edges.
I thought you always see the foreshortened weird.
Now, on an oblique plane, you never see an edge,
Yeah,
and
never
it
see it.
appears foreshortened in all views,
Well, that's what you
because,
said.
like Sean said, it's not perpendicular to any line of sight created by the glass box, or our 6 views. Missy, what's a adjacent view?
It is two views that share the same edge. No.
Very close, very close. No, they do share an edge. They share an edge like a fold line, right?
Yeah.
Like a fold line, so they sit next to each other. So 2 views that sit next to each other, and then what other thing goes on with those?
Like they share the same dimensions.
Yes, they have to have a common dimension. Okay? And according to the glass box, no matter how you set it up, you have any 2 views that sit next to each other, they will share a common dimension. They will. It'll either be height, width, or depth, okay? Depending on which way we go. One, how about a related view?
Maybe like with the right view to the front view or the one next to it.
Yes, the last part. Yeah, a related view. Okay, so you're saying like the top and the right side are related, correct?
Yeah.
Okay, and you're right there on it. I think you know what it is. You just haven't stated it in the terms. So let's throw the definition out there as I put it out in front of you folks the other day. Related view, two views that share a common dimension and are adjacent to the same view. So if you look at the glass box on page 499, just real quickly, I'll zip there so we can kind of look at these. According to that terminology, okay, keep in mind, an adjacent view, two views sit next to each other like these two, share a common dimension. Related views, two views that are adjacent to the same and share a common dimension. Top and right are related because they both are adjacent to the front and they share the depth dimension. Now, why is those things important? They're important because of the rules of orthographic projection. Remember, rule 1 applies strictly to adjacent views. We can project into any view that's adjacent to us with a parallel projector. On a related view, we can transfer those measurements that are common, in the case I just gave you, depth for the top and right, and we can use a meter line or a fold line to transfer those dimensions. That's rule 2 of orthographic projection. That's really why those definitions are important. They're going to transition back to how we technically build these. All right, I think back row just got picked on today, so we'll stop there. Now, just remember, just a quick review. Who picks the front view?
We
You do.
You do, okay? And what's the criteria you use to pick the front view?
most complicated geometry.
Okay. Number 1, as it's seen in production. Number 2, difficult geometry parallel to the front view. Okay, so the first one helps our readers, which are really important people in the equation. So that's our first mandate. Really, our time is not as valuable as theirs. Let's say it straight up. That's what we need to do, okay, to get the thing across and built correctly. But if we don't know how it's used in production, then let's help ourselves. Let's put that difficult geometry in that front view so we're not typically drawing ellipses. And that's really kind of where the problems come. Now, keep in mind, we said that once you pick the front view, all the other views are then set for you based on this glass box right here. Okay, so you don't have a choice on where you're placing them. They will always line up. They'll be in this configuration that goes on. Now, if you're going to go do this and you want to know how difficult geometry kind of looks, it helps if you can look and identify a 3D primitive and know what it's going to project as. And your author gives you a pretty good page on this. Real quickly, before we jump into circles, I want to go look at this. Let's look at figure 1031. When we talk about 1031, we mentioned picking those views. These are really examples of one view drawings right here. And keep in mind, we only have one view drawings when we know who our readers are and they can get there. And they're pretty simple devices, like a washer. Hey, what's a piece of washer? It's basically a chunk of metal, one positive cylinder, one negative cylinder. We don't need a third view for that. By the way, these things right here, they keep one of our largest manufacturing plants in Twin going. I mean, really, this is the bread and butter for Seastrom Manufacturing. They sell these things all over the world, make them right here in Twin. They sell them for 2 pennies. They probably make a portion of a penny for each one, but they make $1 million a day. You know, maybe not quite that many, but they make a lot. You ought to see their automatic stampers in there. Maybe we'll go tour them later. But those washers are just flying off there so fast it looks like a stream of water. Some of the automated machinery they have. And that's their bread and butter. Kind of like in the civil industry, subdivisions, that's their bread and butter. Architectural, banks are their bread and butter. That's how they keep themselves afloat. A bushy, just a metal spacer. Sphere, generally a one-view drawing, although technically it requires 2, but it never changes from view to view. Sphere, perfect circle. PC boards, we rarely give 3 view for that. And again, we have a company in Idaho that makes their living on these types of things. I have several of them actually now. So those are one views. Now, to get it, let's go, there's another page. I'll write down this page number. Yeah, figure 1047. This is a good page to kind of get familiar with, because you're going to basically, once you recognize a 3D shape, you'll know how it's going to project based on whether you put it in the front view in this orientation or the right side or whatever the case might be. So this page comes through with just some of your basic 3D primitives and how it always projects. Okay. So a cube is the first one. Okay. Now keep in mind, they give you 3 views on here. Most of these require 2 of them, not all 3, to accurately describe the geometry. Okay, so like when we're looking at a prism, we need height, width, depth of it. They're rectangles. I need this view and this view, or this view and this view. I don't need all 3 of them, but that's the way they will project. When I come to a cone, again, they give you all 3. Which 2 do I need to accurately describe the geometry of a cone? I need the circular view, and I need the profile view. And that totally describes it. So I would not produce this right side view unless other geometry on the object required it. But for that, that's all I need. The sphere here, you see the 3, that's why that's a 1 view drawing, because all 3 are the same. Now, it does have to have a note, like we looked on the other one, it had a note that said sphere on it. We have to tell them that it's going to appear that way, because this can be more than a sphere with a 1 view drawing. Pyramids, again, you need 2 views. Cylinder, 2 views. But which 2 do you need? These 2 aren't helping me. I need the circular view and the rectangular view of all cylinders. And that's going to be what we really kind of focus on today once we get out this page. So keep in mind, cylinders, we have 2 types. You have a positive cylinder and a negative cylinder. What's a negative cylinder?
A hole?
Yeah, we have all kinds of negative shapes, but cylinders, we get a lot of them. Negative, it always means that that has been removed from the object, or it's got the shape, but it's hollow, has no mass. Then you can also have a positive cylinder, like a pencil, where you do have mass for the cylinder. But you always need circular and rectangular view. Here they're coming in showing 2 prisms together, how they would then project again. You only need 2 of the 3. Then you got cones, spheres, partial cylinders. The bottom one, the bottom 2, they start mixing these items together. Where here they have cylinders and prisms. Now, let's look at the prism and cylinder. Which 2 are required on there?
The front and
Top and front.
Yeah, front and top. Okay, good. You're all kind of picking up that fairly. The right one's not required. Now, keep in mind, why has it got to be the top and front?
You need the circle.
Yeah, you've got to have that circular view of that cylinder that's driving that. Okay. And then you get the rectangular view of the cylinder, and then we look at the prism. So again, break these things down. Look at them. Don't look at the whole object. Look at individual components of it, and then describe those components. At the end of all that, you've got the whole thing drawn. So some good examples on that page
Yeah,
for
I
you
have
to look at.
a question.
Sure, shoot.
So the difference in just knowing, just looking at those drawings, and those hidden lines show that the hole goes through,
Mhm.
and that one doesn't, that's why you know it sticks on top? I mean, if you were.
Right. So this would be a positive cylinder because it has mass.
And then that's, the line showing through says it's negative.
This one, since it's going through, this is a negative cylinder or a hole. Okay. I just wanted to point out that page as we go to it. Let's go to page 525. Now, as we talk about circular shapes, we have quite a few different types of circular shapes that have specific jobs, and we want to be able to recognize those. Okay, first off, whenever we deal with a circular shape, keep in mind we describe it with an object line that we call a limiting element. And what that is basically a line that describes the quadrant locations or where the cylinder leaves our line of sight as it goes around. Because there is no plane change with a circular object. And so we've got to somehow describe that. We call it a limiting element. Use an object line for this. It is not a thin line, it's our main object line that we use for that. So that's the first thing. Now, the second thing is what happens when we come in with circles that are tangent to linear features. We have a convention, remember, a break from a standard, conventions, that allows us to draw these and give that description as it goes. Okay, so we're going to help our readers out here. So in essence, if I have a cylinder that comes in tangent to a linear feature like occurs right here, in essence there is a plane change. We're going from a curved plane to a linear plane. But if it comes in tangent, we do not project that plane change. So we leave that line out. And normally we'd come in and draw that line right there because I'm switching from curved to linear. We leave it off to describe to the reader, this is coming in tangent. Therefore, you now know how to locate the center of it. Remember, tangent circles are mostly self-locating, right? As you found out through your worksheets. Okay. That's how we tell them that. Case in point, here's where one comes in. You can see it's a definite break. It does not come in at a tangent point. Then we do describe that plane change. And we put an object line on there for that description. So, the tangent deal, do not project a tangent plane change. Yes, Cheryl?
Would you define the limiting element again?
Limiting element's a line that represents where a curved feature leaves our line of sight. Okay?
So it's actually that line that's not behind.
Right. So if I'm sitting here looking at this, it doesn't matter which orientation. Here's a cylinder right here. Okay. So it doesn't matter which way I look at it. At some point in time, right on the top, which is generally what we'd call a quadrant location, I can't see the backside. Remember, I'm at infinity. Okay. So I can't kind of do this. I'm at infinity. I have no choice. Limiting element describes, and we usually do that from the quadrant locations.
It's sort of like a horizon.
It's almost identical to a horizon, because the Earth is what, a sphere, somewhat, and it's the same thing, yeah. I mean, go to Nebraska. I always laugh about this. I have a brother-in-law who lived in Nebraska. He used to tell me, Nebraska is so flat I can see the back of my head. But it can't be because it's got the curvature of the Earth, right? So anytime you look at a large body of water or something, that's where it's most apparent. Does that answer your question, Cheryl?
Yes, but you don't, to actually say it, you don't say where the surface leaves your view, you don't, it doesn't actually, where the geometry leaves the view? Where the
curved feature leaves your line of sight as you're looking at it. I don't know another way to say that. I'm not.
That's as good as you could expect, I think.
Yeah. That's good.
Are we good on that one?
Thank you.
Okay. So now, are we good on the tangent convention? Okay. Now I do need to correct one thing. So when we're talking cylinders, this figure right here, figure 10.54, is wrong. I'm going to show you why. In essence, when we are looking at cylinders, what this basic statement says, if I have a cylinder and I'm looking parallel to its long axis, okay, so keep in mind that there is a cylinder that comes out right here, and all this, the author's just giving you the edge view. And he's saying, I'm looking perpendicular to this line of sight, I will get a circle. And yes, that is true. Now, where the author's got a little bit of a mistake going on, here he's got the same cylinder. We're still looking parallel to the long axis, right? The long axis runs this way. And he's saying you're going to get an ellipse. No, you're not. You're going to get a circle. Here, they tilt it again, a truncated cylinder. They say, okay, we're still looking parallel to that long axis right here. You're going to get an ellipse. No, you're not. You're going to get a circle. And this one, same thing. Whenever you look at any cylinder parallel to its long axis, it will always appear as a circle. Always. Now that changes a little bit as our angle of view changes. Now I'm going to switch to the computer on this because it's kind of hard to describe it. I think it's better to show it. There's really two situations we got to be aware of. Juan, would you mind hitting the light real quick? Okay. So I set 3 cylinders up here, identical to how the text was just described. I didn't do the flat one. So I've got one cut on a fairly shallow angle. I think I did 70, whatever the book had. This one's 45, and this one is the other one, I think 30 degrees, something like that. Now, when I look at this way, you see the cuts. I'm going to switch this to where we are looking parallel to the long axis. And the long axis is running right here like my cursor shows, right? That's the long axis. Okay, now let's go look at these where I'm looking parallel to the long axis. So I come here and look at those 3. How do they all appear? They're circles. And in fact, if I went and projected this, had AutoCAD run the 2D drawings, they would be perfect circles. And it doesn't matter the angle of the cut. Whenever you look parallel to the long axis, it will always be a circle. Now that changes when we go to different views. Now most of the time, the other view we get of truncated cylinders is usually perpendicular to those long axes. Okay. So just to show you the view I'm going to give you, I'm going to go right back to the text real quick. So these are all looking perpendicular. Now what if we come and we look 90 degrees? Because remember, we get to pick that front view. This guy's probably sitting in our front view because we want to draw circles. Okay? We got templates for them, we got the circle commands, real easy. Now, that's my front view. Keep in mind, I go to a top view, I'm going to be looking perpendicular to that long axis, right? If I go to my right side view, I'm going to be looking at it in profile. Then it's just a line. But it's that other one where it appears foreshortened that gives us a little bit of a problem. Okay? And let's look at that. Because there's 3 cases on it. So I'm going to go back to the computer. So this is my front view that we just talked about. Truncated cylinder always appears as a circle. Now, what if I then go and say, well, I've got to produce a top view of these. Remember, this one's got the shallow cut. This one's the 45-degree cut. This is the deep cut. In fact, I'll go back to that real quick and show you. There's the cuts. Now, let's go to the top view on this. Okay. So there's, you see how they project. The shallow cut has an ellipse with the major axis running horizontal, vertical axis being our minor. This is elliptical. Keep in mind, the angle of the cut here was very steep. It was over 45 degrees. On the 45-degree cut, how does that one appear?
Almost circular?
No, not almost. Take that word almost off of there.
Circular?
It is a circle. Okay. If the cut of the cylinder is 45 degrees, and you look perpendicular to that long axis, it will always project as a circle. Remember that 45, 45, 90 triangle I talked about, where the legs are always equal? It's the exact same case. That's why it projects as a circle. This guy's a circle. This one again will be an ellipse. It will be rotated where now my major axis is vertical, my minor axis is horizontal.
And
So-
that was the,
That's the shallow cut, or the one that is greater than 45 degrees. So here's the case, folks. Whenever you have a cylinder that is truncated and you look parallel to the long axis, always going to be a circle. If you have a truncated cylinder and the cut is 45 degrees, if you look perpendicular to that axis, it's still a circle. All other cases, it's elliptical. All other cases. So I just wanted to kind of clarify that picture. Now, just to show you, if I take this thing and I kind of flip it up and start looking, I mean, how are all those looking? Now I'm not looking, oh, what'd I do? Okay, here I'm not looking perpendicular or parallel to the long axis. They're all elliptical. Doesn't matter what angle I take it to, no matter what, you will get ellipses. But luckily, we get to set these up, so we pick how we look at it.
So if the cut was straight and you looked at it on angle, would it still be like?
Still be elliptical. The only time it will appear circular, even straight, is when I look parallel or perpendicular to the long axis. Well, in your case, you said a straight one. Perpendicular will always project in a line. Yeah, a good exercise on this, besides looking at these solids I've got on the computer, is grab a piece of clay, roll it into the shape of a cylinder, cut it at any angle, and start spinning that thing around, see what you get.
So then how would you draw that middle of the 45-degree cut? You're doing, not doing, it's gonna be a circle, how, you know, where do you put the line? Showing the angle.
If you get to a right side view, that's where it would be. So if in the front, it was a circle, because you're looking
Yeah.
parallel to it, and then you go to the top, it still appears as a circle.
You're right.
You'd have to go to the right side to see it in profile. All right, so that kind of explains, I think, that figure. Any questions on that? You all good on that?
Yeah.
All right, very important page for you, page 527.